Welcome to Advanced Topics in Cognitive Science. My name is Dr. Ben Harvey, you can call me Ben. We've got a very full class this year, so if you've got an empty seat next to you, prepare for it to get filled. If you're coming in late, there's some more chairs over at the front here for anyone that overflows the chairs that we have. So many of you have already met me. I taught parts of Chris Jansen's course on cognitive modelling a couple of periods ago. So I'd like to start this class by going through the outline of the course so that you know what to expect and also what we expect of you. So some of this lecture content is very complicated, all right? And you guys all come from very different backgrounds. We know that the AI Masters program is a very diverse pool of students, right? But the content in this lecture is going to be examined. All right, even though it's quite complex and will be quite new to a lot of you. And you need to pass this exam to pass the course. So we're going to go through it slowly, and we're going to start from first principles for those of you that don't know anything about it. So for those of you that know a bit about deep learning already, this first class particularly will be a bit slow for you. And for those of you that it's completely new, hopefully you don't get too confused by it. All right. So please ask questions when you don't understand anything. The explanations and the discussions that we have as a result of you guys asking questions have been very useful for the course in the past because it helps me understand where you guys are as well. Okay, so the main goal of this course is to explore the relationship between cognitive science and artificial intelligence. All right. So we're going to focus on deep learning in artificial neural networks and on the comparison between these artificial neural networks and biological systems. All right. So we're going to see what the principles of deep learning are, but then what may be less familiar to you guys, because this is a course on cognition as well, we're going to look at which biological processes in the brain deep convolutional neural networks imitate. Okay. We're going to see what in the brain is missing in artificial networks. And that allows us to see what might make artificial deep learning or machine learning more like biological systems. All right. So at the moment we're going to examine really where the cutting edge is in deep learning at the moment. But we expect most of the things that deep learning doesn't do, that biological systems do, to be kind of future directions in deep learning. And that will become, that's a very vague statement, but it will become clearer what I'm talking about later. As well as this, we want you to be familiar with the use of artificial intelligence in cognitive science research. I know a lot of you have come from a cognitive science background. And then in the labs, we're going to get you to build something. Right? So we're going to get you to build some deep learning networks to do relatively human-like tasks. So specifically tasks in visual object recognition and in natural language processing. All right. You're going to be assessed on this in a couple of ways. So first of all, you're going to do some lab assignments. All right. So we do this in pairs. And you guys are going to complete 2 lab assignments, one in the first half of the course on visual processing and one in the second half on natural language processing. And in these, you're going to build simple deep learning networks to solve computer vision and linguistics tasks. And here you're going to be graded on the written reports that you produce as a result of this. And your grades are going to depend on the depth of your answers and how complete your work is. All right? And each of these 2 halves forms 30% of your final grade. All right? Second, we're going to have an exam right at the end of the course. Okay? So this is going to examine your understanding of the lectures and also of the reading assignments which you can find in the syllabus. And so that determines altogether 40% of your final grade. And importantly, you're required to pass this exam to pass the course. In previous years, people have done rather better on the labs than on the exams. So we have an exam that you have to pass the course. We're going to have 2 classes each week, and these are split into lectures and labs primarily, with one of the classes reserved for an exam at the end. So in the first 4 classes, we're going to have 4 lectures, So these are these first 4 classes here. These are 4 lectures from me. And then also mixed in with these, we're going to have kind of sessions where you can start up doing the first lab. All right. So that's basically because our Wednesday class is a 2-hour class, but our Friday class is a 4-hour class. You can't do 4 hours of lectures, it's just crazy. So we'll give you 2 hours of lectures and then 2 hours of starting on the lab, and then again go back to lectures for the next class, and then next Friday continue on the lab, and then keep going through the labs. In the second half of the class, it's a bit more evenly split between lectures and labs. The lectures continue because of the structure of the labs, basically. Some of the more advanced concepts are introduced later before the end of the labs. Okay. All right, so, oh yeah, a couple of things about this. First of all, you should notice that the Friday classes start at 9:15. Nobody likes starting at 9, everybody comes late, so we start at 9:15. That's just a practical thing, it makes everybody's life a lot easier, including my own. The second thing to notice is that the exam at the end here does actually start at 9. All right, so that's going to be, I'll remind you of that several times as we approach the exam. All right, and that's just because it's when we could get the room for a decent amount of time, and we start at 9. All right, so just remember that. I'm going to remind you of that a number of times. Okay, so this course looks at 2 different topics. It looks at visual processing and language processing. But what brings these 2 topics together is that they're both important goals of modern deep learning research. Okay, so research with deep convolutional neural networks. So a lot of the commonality between these 2 topics is really about the research method, deep learning. Okay. So why deep learning? Why is deep learning such a big deal for us? Why do we focus so much on that specific machine learning method? Well, artificial intelligence has made great advances over the years in doing certain types of tasks. All right? So tasks that can be described by simple mathematical rules, okay, are pretty straightforward for most artificial intelligence systems. And indeed, if it's governed by simple mathematical rules, you should be able to just program an algorithm that does it without needing any machine learning at all. Okay. And tasks like this, these sort of mathematically formalizable, non-NP hard tasks, are relatively simple for computers to do. On the other hand, they're relatively difficult for humans to do. So, you know, people often ask me, when will a computer system become as intelligent as a human? And I would say that happened a very long time ago in the domain of linear algebra. So if you just want to do calculations, get your computer to do it. It will be a lot faster and a lot more accurate than a human can do it. All right? So tasks like this are very well suited to computers and relatively poorly suited to humans, on the other hand. But AI has been less effective in a different type of tasks. So these are tasks that are generally hard or impossible to describe using formal mathematical rules. All right? But on the other hand, they're tasks that are relatively easy for humans to perform. And when you ask a human, unfortunately, how we perform these tasks, we tend to say we do it intuitively, or we do it automatically, and we're not really aware of how we're doing it. All right? We're not breaking it down into subparts and thinking through these tasks. All right? So we generally think of them, as humans, we think of these as being intuitive or automatic, but they've been very, very difficult for computers to do. Okay? So what type of task is that? Well, one type of task is visual object recognition. All right? So, of course, for Google, for example, it's very good to be able to look at the images on the internet and know what those are pictures of, because it lets you do Google image search. All right? That's been traditionally a very difficult thing to do. Now Google does that with deep learning. Another such type of task is things like automated driving. Right? In automated driving, well, humans find driving relatively easy to do. You can learn to do it. But if you're asked how you're doing it, it's very, very difficult to explain to somebody how you're driving. And it's even harder to explain that in an algorithm so that a computer can do what the human's doing. Right? So that's a very, very difficult task for a computer to do that's relatively easy for a human to do. Not that easy for a human. But again, it's a very useful application of deep convolutional neural networks. This picture is meant to represent text analysis. Okay, so if we see some document of text like this, we can pull out important information, all right, and we can categorize which people this is talking about, which companies this is talking about. And, well, various types of business stuff are used in this example. But more importantly, we can understand what text or what spoken language is about. We can do natural language processing. So this is the topic of the second half of the course. All right. And finally, there's a certain class of games that humans find, I hate to say relatively easy because I'm using Go as an example, which is a fiendishly difficult game, but the way people describe themselves playing it is intuitive. All right? And very recently, artificial deep convolutional neural network has become the best Go player in the world. All right? And that only just happened. So these are all tasks that, what is common about them is that they're, I say easy loosely, but relatively easy for humans and extremely difficult for computers. And computers have traditionally performed very badly at these tasks. Generally, actually, old computing systems playing Go can beat me, but that's because I'm not very good at it, right? But they're not world class. Whereas computers playing chess, which don't rely on any complicated machine learning to do it, well, simpler machine learning to do it, have been able to beat humans at chess for a very long time now. Okay, so what is the approach that's taken in deep learning? Well, effectively, deep learning is a form of machine learning. So deep learning learns from experience. All right, it's doing some transformation of data without any formal rules of what those transformations are. It doesn't have a knowledge base, right? It doesn't have any logical inference involved, right? It has to figure out the rules of the game for itself. It has to figure out how to solve its task without precise instructions. So all of the way it does this is using machine learning. And the real important insight that deep learning has provided is it uses a hierarchy of concepts that are each transformations of each other. Okay. So basically, the layers of a deep convolutional neural network, which is a topic we'll come back to a lot, each analyze the output of a previous layer. Okay. And the lower layers of the network, the simpler layers of the network, are analyzing relatively simple concepts. But as we go higher and higher in the network, each of the concepts represented in each of the layers becomes more and more complicated and more abstracted. So each concept is not defined by its relationship to the inputs, but instead by its relationship to earlier, simpler concepts in lower levels of the network. Right. So that is to say that the network is building complicated concepts out of simpler concepts. Right. And then hierarchically doing that, so then analysing those more complex concepts to make yet more complex concepts, and so on. So this is exactly what a human is doing when we're learning about the world. We're learning the simple concepts, we're learning the colours and the shapes that we're seeing, and we're building up into a more complex representation of the objects we're seeing and how we interact with them, and so on. So the main inspiration for all of this is the brain. This is exactly what the brain is doing, and that's what we're going to investigate in these first classes. All right. So, here I've talked in a very loose way about concepts, but to put that in a slightly more concrete term, okay, what we often talk about in deep convolutional neural networks is that each layer has some representation of the input. And the performance of the system depends on the representation of the thing it's trying to classify. Right? So if a machine learning system generally, okay, is trying to give the right answer to a question, right, it has to represent the data in such a way that that answer is clear in the data, is represented in the data. Okay? And so that depends on getting the information that the computer's been given and transforming it into a way that gives the answer. All right? So again, that's we'll see some more concrete examples of this in a minute. So each piece of input information is generally referred to in deep convolutional neural networks as a feature. Okay? And the same feature can be represented in different formats. Okay? And it's often easy to convert between these formats. So far I've described this in very loose, abstract terms. Okay? But here's a really concrete example. So here we've got two groups of dots. Right? We've got green dots and we've got blue dots. And if we want to separate those, right, by a single line, we cannot do that. Right? There's no line that we can draw that meaningfully separates these two groups of dots. Right? However, if at the moment these dots' positions are represented in terms of x and y positions, so Cartesian coordinates. All right? But that's not the only possible coordinate system. Right? We can transform this into a polar coordinate system, so that instead of representing x and y, we represent polar angle, that is to say how far we are around the image, and we represent eccentricity, that is how far we are from the centre of the image. Right? So if we transform this into this, right, then this is the polar angle, sorry, this is the eccentricity, and this is the polar angle. Yeah? Okay. Then we can draw a line that clearly separates these. All right? So transforming the data allows the computer system then to separate the two different sets with a really easy transformation, with a really easy decision. Okay, is it on this side or is it on this side? Okay. But there's no easy way to separate the data here. Okay, so you have to transform it first before you can separate it. So a simple task like this, therefore, can be solved by choosing the right set of features, which in this case are polar angle and eccentricity. Okay, with very minimal learning necessary in this case. Right? However, for many tasks, it's hard to know which features or formats are the most important to determine the output. Okay? And many of these may be kind of high-level features, which are kind of abstract features, that need to be extracted from the input data first. Okay? So we've chosen a really simple example here. But generally what deep learning is trying to do is to transform the input in such a way that a decision can be made straightforward. Okay. So deep learning, therefore, aims to extract the important features, right, and determine which features are important through experience. Okay. So therefore, the chosen format of the data strongly affects the difficulty of the task. So what a deep convolutional neural network is trying to do is to transform the data to make the task easy. So if we look at the representation in deep convolutional neural networks, the useful features for actually doing the task may need to be transformed or extracted first. Okay. So deep convolutional neural networks have multiple representations of the input. Okay, with different levels of abstraction. And each of these representations is built from the immediately preceding representation. So it's built from a simpler representation. So what this can do then is it can transform features into a different format before learning their link to the desired output. Okay. It can extract complex features from simpler features. Right. And essentially it's doing this using multiple steps. Right. So essentially these transformations that we're doing can be seen as being a bit like multiple steps in an algorithm. All right? It's just that the algorithm has to be learned. So the algorithm itself is the goal for deep learning. So each layer in a deep convolutional neural network can be seen as the computer's memory state after executing one set of instructions. And deeper networks with more layers, therefore, are executing more instructions, more transformations in the data in a sequence before they're making a decision. Okay. Just like in a regular computer program, a regular algorithm that you might code yourself, right, the individual steps here are generally extremely simple. Okay? But what they're achieving in the end could be extremely complicated. That's kind of how we get to this thing of being able to get a really simple set of rules, apply them to a set of inputs, and be able to do something that's traditionally been very, very hard for computers to do by having these lots of different sequential transformations of the data. So this is an example from object recognition. Okay, and we're going to return to the example of object recognition lots of times in this course. And it's a really good example, object recognition, of a process that we find intuitive or automatic, but is extremely hard to formalize into a program. It's also a very useful thing for computers to be able to do, okay, so that we can find images on the internet without human labeling all of the content. But more or less how this would go in a deep convolutional neural network. This is a very, very simplified version of this, just to kind of outline what I've been talking about so far. Is we start with the inverse, right? So we start with the color in every pixel, for example. Right? The first layer of the networks looks at the relationships between these neighboring pixels to pull out features like edges, so really simple features. Right? And in this case, just horizontal and vertical edges, so really, really simple things. The second layer of the network then analyzes, doesn't look at this, right? It doesn't look back at the individual pixels. It looks at the edges in the first layer of the network. Okay? Then it analyzes the patterns in those to pull out more complicated features. So things like corners and contours and curves, right, that are not represented in this layer. Then the layer after that, the third layer in this case, looks at these contours and corners. And again, doesn't look at this and doesn't look at this. It looks at the immediately preceding layer, so that it can pull out more complicated parts, so conjunctions of corners and contours that make up basically parts of objects. Right? And then the top layer, the output layer here, can analyze these different object parts to determine the identity of the object. Right? So very importantly, the real insight here, right, is that each layer is just looking at the previous one, and it's doing something pretty simple to transform the previous layer. But it's coming to a very, very complex representation, a very abstract representation, very quickly, that makes the task that it's trying to do relatively simple. So if you know what object parts are available, it's really easy to classify what the object is. So this is basically why deep convolutional neural networks. This is why they're important. This is the trick that they're doing, and what makes them useful. Okay. Now, just as a quick side note, all right, quick note on notes. I see a lot of you taking notes, that's good. All of these slides are available online already. They're on the Blackboard. I normally put them on the Blackboard just before I give the class, okay, because I'm normally working on them till the last minute. But you will see that there's very little text on my slides. Okay. And this works well in class, but it does make my slides very difficult to study from. Right. I deal with this in two different ways. First of all, my online slides don't just look like this, they also look like this. So this is everything I said about this slide. So this is pretty much a script of what I'm saying. And so this is a pretty complete description of what I'm saying, which makes studying from this much, much easier, this format. You can see this if you look on Blackboard. Second, I'm recording this lecture. I'm recording all of my lectures, and I put these movies up on Blackboard. Okay, so this can help you to study as well. Right. So, yeah, this should make it easier for you to, as I say, this is pretty complex content for a lot of you, and you really want to be able to focus, right? So I don't want you focusing on making notes. I want you to focus on what I'm saying so that you can try to follow it, knowing that what I'm saying is already written down for you. Okay. So what is useful for you to do when taking notes, though, is to take notes on what you think is important, to kind of underline the main points. Right. I try to do that to some extent. Also, take notes on content that won't really copy into a PDF. Okay, so like a movie is not going to be in the PDFs. Okay, it will be in the movies. Now, finally, you are allowed to use laptops in our lectures. I see many of you are doing it, but I don't recommend it for one simple reason. I'm a psychologist, so this is my reason. This is the effect of using laptops in class on exam performance, right? And using laptops in class drops people's exam performance by about 10%. Right? This is a pretty well-established finding. So this multitasking that you think you're doing, looking at your laptop and listening to me, you're not. You're actually doing one task at a time, transferring between them and doing both of them badly. Right? People can't multitask. Also, having other people using computers in class. So even being able to see other people's computers is sufficiently distracting to significantly affect your grade, which is the other reason why I've kind of tried to discourage people from doing it. Similarly, phones, put your phone away. This is the effect of where your phone is on the grade that people get in classes from a very similar study. Even having the phone in your bag, right, rather than being off and in another room, significantly affects people's performance in standardized tests. Okay, so what I suggest instead is making notes on paper, right? These slides should have numbers on them. I noticed that they actually don't. I'll put numbers on them during the break. But you can either print out the slides or use them on your computer or whatever. I'm not telling you how to study, all right? But know that what I'm saying and the slide content is available to you. You don't need to write it down, all right? So just focus on understanding it. And where the slides are numbered, which I noticed they're not in this particular case, you can just link your notes to what I'm saying by writing down the slide number. All right, so enough on that. Okay, so a bit more about what a deep network is. We just saw that this is a machine learning network. Well, sorry, this is a learning network that transforms or extracts features using multiple nonlinear transformations of the data, so multiple nonlinear processing units, arranged in multiple layers with a hierarchical organization. Okay? And in these different layers, there are different levels of representation and abstraction. Okay? So this is a generic definition of what deep learning is. Notice, at least as I've written it down, this does not specify machine learning at all. Okay? In this course, we're also going to look at biological neural networks in the brain, which are also deep networks. They just work in a different way. So that's just an introduction of like the whole topic. What are we going to look at, right? But now I'm going to break this down into what our different lectures are going to study. Okay, so my lectures 1 to 4, we're going to start by looking at artificial networks, so machine learning systems. All right? In the second lecture, we're going to compare these to the human brain's biological neurons, okay, which are what these artificial neural networks aim to imitate. All right? In my last 2 lectures, we're going to look at the stages of visual processing involved in object recognition in both of these systems and to compare them. Okay. And this is also going to show what's missing in current artificial neural networks and how researchers are starting to build deep neural networks that fill in these gaps, so that act more like a biological neural network. So we're going to begin by looking at what machine learning is, starting artificial networks from the very start, because I know many of you are very familiar with this, all right, but some of you aren't. Okay. So what is machine learning? It is the field of science that aims to give computers the ability to learn without being explicitly programmed. Okay. This definition comes from 1959, right? So this is a very old description of what machine learning is. Okay. And Arthur Samuel, who made this definition, showed a machine learning algorithm, many games of checkers or drafts, this game here, okay, to allow that system to learn which board positions were likely to lead to a win in the game. Okay. And the only programmed rule was the way that the pieces are allowed to move. Okay. Now, what this resulted in was a computer system that was able to effectively play checkers by moving from board positions that it knew were associated with losing to board positions that it knew were associated with winning. Okay, by making the very simple moves it was allowed to do. So here you can see the black player, which is a machine learning algorithm, consistently defeating the white player, which is moving randomly. Okay. So this is a really, really simple example of some machine learning. One of the earliest examples, playing a very, very simple game. Okay. But if we look at this definition is kind of lacking. This definition of machine learning uses the word learn without any definitions. Okay? It also uses the word computer, which is a synonym for machine. So basically it's saying machine learning is letting machines learn, which doesn't really say anything. Right? So this is actually a really, really poor definition. Okay? It gives the gist of what we're talking about, right? But actually what it's saying is not really getting to the core of what's happening. Okay? Tom Mitchell provided a much more useful definition in the 90s. And he said that a computer program is said to learn from experience E with respect to some class of task T if its performance measured by P improves with experience T, with experience E, sorry. Okay. So that is to say that machine learning is happening if performance in a task improves with more experience of that task. Okay. That's a much more useful definition. So this is expressed in organizational terms rather than in cognitive terms. So what I mean by that is it's not saying a machine can learn if a machine can learn, right? Because learn is a human construct, right? Experience is giving more data, right? Performance is doing better at performing the task, right? These are not human constructs so much, right? A similar way of seeing this, right, is the Turing test, right? The Turing test doesn't ask, can machines think, right? It says, can a machine do what we can do, right? Can I tell the difference between talking to a machine and talking to a human, right? We know that a human can think. If I can't tell the difference between a human and a machine, then it doesn't matter if the machine is thinking or not, right? It's doing the same thing as someone that can think is doing. So this is a very, very similar type of definition. It's saying what we would expect to observe, not what the process involved is. All right, so if we look at this definition again and we actually apply a concrete example to this, all right? So learning to filter spam, right? What is the task here? That is classify which emails are wanted, not spam, versus which emails are unwanted, that is spam, right? The experience that we train this on is watching a human label emails, that is a training set. Okay? Performance is the proportion of new emails in a test set that is correctly classified. All right? So this gives a very clear example of something that we all see computers doing a lot. Right? And so this is a relatively simple machine learning example, and this can be done without deep learning. Increasingly it is done with deep learning, particularly by Google. And so we have an example of what machine learning is. So how does machine deep learning work? Okay. So we've seen this definition before. So a learning network, a deep network is a learning network that transforms or extracts features using multiple nonlinear processing units arranged in multiple layers with hierarchical organization and different levels of representation and abstraction. So this is a really broad definition, so we're going to use, again, an example to see what this actually looks like. And the example that we're going to use in the first half of this course is object recognition. Right. So object recognition has been a major goal for deep learning in recent years, and so we can therefore investigate in quite some depth how this has been done. Right? It's been solved, basically. Right? So object recognition may sound like a relatively easy problem for computers, but it's actually really, really difficult. So if we see what happens if I type cat into Google, right? I get lots of images, they're all cats, but they don't look similar, right? These images, they're similar to a human because they all contain cats, right? But a computer doesn't know that they all contain cats without learning that first, right? So they don't actually look similar, right? So for example, this has no background and a black animal, right? This has just a little bit of face, right? With very little contrast to the background. So the identity of any object that we see actually has really very little relationship to its impression on the retina, or at least a very complex relationship to its impression on the retina. So this result was achieved by using an artificial deep network trained for object recognition. And for this network, and also for human vision, objects can be recognized from different viewpoints So we see these animals from lots of different viewing angles, all right, at different sizes, in different positions in the image, right, with different lighting conditions and different backgrounds. So despite the fact that all of these images look really different, right, the computer system has learned to get rid of all the differences and focus on what's similar. In the back. We're talking about AlexNet specifically, yeah. So that's. But I expect Google, you know, somewhere in secret, has much more advanced versions of AlexNet-like things. But AlexNet was cutting edge when I wrote this. So in this, all of these images are in the same class, right? They're all pictures of cats. Okay, but objects, images in the same class can look very, very different from each other. Okay, so you might think that we could solve this because cats have pointy ears, right? But if we look at these examples, we can see plenty of examples where there are things that are recognized as cats but don't have pointy ears. Right? So we can't directly recognize an object from its impression on the retina. We need to do something really complicated that's actually really difficult to get your head around. So people have been thinking about this as being a multi-level problem for many, many years now. So this kind of viewpoint was proposed by David Marr back in the 80s. And what he basically said was, what you do is, this is much like we described for that picture we saw earlier. We get an image, we break it down into its local features. Right? So we, first of all, make a sort of a representation of the local image properties in different parts of the image. Okay? Then we analyze those local features to pull out the shapes in the image. Okay? So stage 2 then is building a representation of larger scale surfaces and shapes. Stage 3 then analyzes that representation of shapes to determine what type of object it's looking at. So it matches shapes and surfaces with stored representations of objects. So this approach, though it's very outdated, is already a multi-layered hierarchical approach. Here's how this might be, again, built up in kind of simple terms using biological neurons in this case. So we might start with neurons that can respond to a vertical edge. All right? So this neuron likes vertical edges in a particular position. This one likes horizontal edges. So if we feed them both into a later neuron, right, that takes inputs from both of them and will only respond if both of these are responding, this neuron will then respond to corners. Right? Okay. So if we've then got a neuron that responds to corners and somehow we've, over here, determined some representation of length, right, then putting together a group of corners and a particular length of the edges between them might tell us that we have a rectangular surface. So that's a kind of component part. Right? If we put that rectangular surface together with some legs, that again has been done by a network over here that we're not seeing, right, that might tell us that we've got a table. Okay. So we might, seems quite sensible, and indeed is the type of idea that a deep convolutional neural network is built on. Right? But we might think that therefore we could build up an object recognition system, object representation, from combinations of feature representations like these. Okay. And indeed, many objects are built from parts, right? A table is built from a rectangular top with some corners and some legs. Right? So we might think that simplified parts, if we build a representation of the parts that things are made of, right, and we know what that part looks like from any angle, okay, then we could determine what an object would look like from any angle. Okay? That seems pretty sensible. Right? So that's basically the same thing, but representing everything as a three-dimensional object rather than an image. Right? So you could do that as well. However, no one's ever made a program that does this successfully. Right? So you can break this down into a relatively simple algorithm, but no one's ever made an algorithm that can do this. Not for lack of trying. All right? People were trying to do this for 20 years and never achieved anything like it. Okay. So it seems like the features that are considered in this model, right, are too human. All right? A human sees an edge and a corner and and a set of corners and thinks those are things, right? But that's the limit. That's the way that we think, right? What our brain is doing to do that is a different question. These parts that we're building up here are just too human, right? When is a feature a corner and when is it a curve? Right? Is there something in between a corner and a curve? Right? Can we define a corner, an edge, or a surface as rigidly as this network attempts to do it? Right? Essentially, all of these steps tend to limit a network to recognize specific examples. Right? If I say, I'm looking for two corners with 90-degree angles between them, right? Then I'm only going to find tables that have square and rectangular tops. Right? Not all tables have square and rectangular tops. Right? So effectively, by building in rules like this, right, you're limiting the network to recognize specific examples that you're thinking about when you program it, right? Rather than to generalize to all possible tables, right, which is the goal of the network here. Okay. A deep convolutional neural network does things in a different way. So basically what it does is instead of programming those rules, it tries to learn the rules. It tries to learn what transformations are going on to achieve each of these steps. So all of these transformations are themselves targets for machine learning. Right? So here we can see a network that, and this comes from one of your reading assignments, takes an input image, okay, does some analysis of different little bits of the image, okay, does some transformations of those, which we can look at this in a lot of detail, okay, and then makes a kind of more abstract representation of what's going on in that image, then a yet more abstract representation, then a yet more abstract representation, and this representation allows us to pick what type of object there is in the image. Okay, so it allows us to perform the task, is there a tree in the image or isn't there a tree in the image? Yeah. Yeah, so this is a more more biologically inspired neural network. So this comes from a paper by Jim DiCarlo and Dan Yeamans, who are researchers from MIT and Stanford, but they're really neuroscientists, right? And this network is very much closely inspired by a biological neural network, which is why it is a bit funny to someone that was designing it from the start. Right? So, if we look at this network, right, this is a learning network that transforms or extracts features, right, so performs lots of different representations of features using multiple nonlinear processing units, which is what this is, okay, arranged in multiple layers, which is what we see here, okay, with a hierarchical organization, which means that one feeds into the next, feeds into the next, feeds into the next, and with different levels of representation and abstraction. So this is going to be like an edge detector, so this isn't going to be very complicated at all, just finding where the edges are. And this is going to be a really abstract representation where if a human looked at it, we'd have a lot of trouble understanding it. Basically what it's doing, it takes an input image and it transforms its features to extract the class of object that the image contains. Okay? And we can see that this is arranged in multiple layers, with one feeding into the next. The last part of this definition is about nonlinear processing units. Okay. So what is that and why is that important? I think we're going to start there because it's kind of the simplest point that we need to understand what this network is doing. Okay. So in a linear function, right, so these are linear functions, okay, the y-axis here is a function of the input, that is, say, the x-axis, right, multiplied by a constant, a, right, and then added to another constant, b. Okay. This multiplier can be positive, can be negative, or it can be 0. Okay, yeah? Right, you are. Indeed, the point I'm making does actually generalize to affine functions. Okay. So, in a nonlinear function, there's a different type of relationship between x and y. Okay. So x is any other type of function of y, okay, that doesn't follow this formula. Okay? So there must still be some relationship. All right? There must be some relationship between the input x and the output y. Okay? That is to say that y must change with x in some predictable way. All right? But we can see that all of these nonlinear functions do things that linear functions cannot do. All right? So they have curves in them, simply. Now, that's the difference between linear and nonlinear functions. Now, why do we need nonlinear functions? Well, linear functions are very limiting. There's some things they can do and a lot of things they can't do. Okay. So here we can see 4 different data sets, all right, that are all fit with the same linear function. They have the same blue line going through them. All right? And in all of these data sets, this blue line is the best linear fit. All right? It's the same blue line. So those have been very carefully curated, but we can see that they're all very different. Okay? The actual data points are really different from each other. So, in fact, these data, they all have similar means. Okay? They have similar standard deviations. They have fairly similar correlation coefficients. All right? And all of these are linear operations. However, the data sets clearly have very different relationships between x and y. This is one type of relationship. This is a different one. This is a different one. They're all different, right? Obviously. So a linear function here is too simple to capture what's going on in the data. Right? So we can see that they're all basically bad descriptions of the data, perhaps except this one. But in the context of deep convolutional neural networks, there's a more important problem with linear and indeed affine functions. Okay? The many layers of a deep network repeatedly perform functions on the output of the previous stages. Okay? So joining these functions together, right? So that does something basically like this, right? What the first layer is doing plus what the second layer is doing, and so on. All right? Joining all of these together basically still produces a linear function. Okay, so it's not transforming the data at all. This becomes a little harder to visualize, all right? But if we just have lots of linear functions that all contribute to the output, right, the same output y, okay, this becomes really problematic because we can have several relevant inputs. Okay? But if we don't have any nonlinear interactions between them, okay, all of these inputs are basically contributing to the same equation. Okay? The same, it always can be simplified to one linear equation. So in this case, for example, we have 2 different things that are contributing. It's hard to show more than 2 because thinking in more than 3 dimensions is very difficult for humans. But if we look at 2 different inputs, right, income and temperature, and then the output being ice cream consumption, right, both of these affect how much ice cream you eat, how much money you've got, and how hot it is. Right? So they all basically can contribute to an equation like this. Right? But that means that we can really this means that this is only ever doing one thing. Right? This equation here can be simplified to, again, a y equals ax plus b equation. Right? That's a problem because it means that in this network, each step, if it's only performing a linear transformation, then it has another linear transformation performed on the output, then another linear transformation performed on that. And all it's doing from this layer, from here to here, can be summarized by one linear transformation. Okay? So that's the problem with linear functions, right? They don't actually change the data, they just rescale the data, basically. So all of these different layers aren't doing anything beyond just rescaling the data in more and more complex ways, but still fundamentally just rescaling the data. So in this network, the inputs are the brightness of the individual pixels here, right? There's no way that you can get all of the brightnesses of these individual pixels, add them together, multiply them by something, and add a constant to them, right, that tells you whether or not it's a tree, right? That's the problem here. Okay? If we're only doing linear transformations, we can get all of these different pixels, put them together however we want, sum them, multiply them by whatever, right? That doesn't tell you whether it's a tree or not. You need to do something more complicated. So, indeed, any operation that can be done with linear functions can be straightforwardly described by formal mathematical rules. Okay? So that's not what we're trying to do with deep convolutional neural networks. So that's a problem. So, at this point, I'm going to take a short break. So let's take a 10-minute break and come back at 4:15, and we'll continue. So, in the example that we're looking at here, we have a complex nonlinear function that contains 4 operations. These are filter, threshold, pool, and normalize. These are not always in this order. These are very important operations to understand, as variants of these are the basic building blocks of pretty much every deep convolutional neural network. So we're going to look at them one at a time. So the output of these here are shown as happening between layers, right? So this is going in between layer 1 and layer 2 here. So the output of one of these functions feeds directly into the next, and the next, and the next. Okay. So, and this is true whether or not these operations are in different layers. So here they're shown as being between 2 layers, right? But you could just as easily say that this operation has another layer here, followed by this operation and another layer here, and so on. All right. So where the layer boundary happens, as we're showing here, is kind of arbitrary. All right. I think this is a good way to describe it, but other people would say that that there are separate layers of the network between each of these functions, which is just as valid a way to think about it. Okay. So there is no step in this sequence, therefore, that has a particularly special status. All right. So repeating these 4 operations effectively forms one layer. Okay. So note that in this description, this group of operations, this group of processes, is described as a linear nonlinear unit, all right, which may be a little bit confusing. The nonlinear function here is the threshold function, this one part here, but the filter, pool, and normalize functions, perhaps not the normalize, are linear. All right? So let's look at these one at a time. So the first of these operations is the filter or convolve step, as it's sometimes called. Okay. The filter or convolve operation is perhaps the most computationally important. Right? So after the first processing layer, the input or source of this, well, maybe let's start a bit earlier on this. Okay. So what we have here is we have an input, let's say image, okay? And these numbers represent the brightness of the pixel in each one of these input, in each pixel, right? Now, this group of pixels here is then going to be multiplied using a matrix multiplication with, using a convolution, technically, is going to be multiplied by this group of pixels here, which is the filter, okay, to produce a single number result. Okay, so what we're doing here is we're getting this group of pixels. We're seeing how well it matches with this filter, right, and producing a result that depends on how well that matches. Right? And if we look at what's going on a bit more carefully, all right, what's happening here is this pixel, okay, this one in the top corner, and this pixel, the one in the top corner of the filter, are being multiplied together. All right, so this is 3 times minus 1, okay? And then that result is being added to this pixel multiplied by this pixel, all right? So 0 times 0, okay? And that's been done for all 9 of these positions, and the results have been added together. So this is a matrix convolution, okay? And the result here is minus 3. So that is to say that this pattern here does not fit well, does not match well with this pattern here. Okay. And more explicitly, if we look at this filter here, this filter has negative numbers, so low numbers on one side, and high numbers on the other side. Whereas if I look at the group of source pixels, on this side, which has low numbers here, it's got higher numbers. And on this side, which has high numbers here, it's got lower numbers, right? So this filter doesn't match this group of source pixels very well at all. So the result is a negative number. That is to say, there's a bad match between them, all right? Okay. Now, this is easiest to understand in terms of this being the pixel intensities in each image. We will see later that this is a very, very limiting description, and also we'll see later that this filter here, while we're showing a very specific type of filter, in this case an edge detector, this filter is normally learned, all right? So it's normally actually the target for the machine learning. So rather than being an edge detector with dark on one side and bright on the other, this is actually this has to be learned instead. In the back. So I'm going to explain this so that it's simple for people to understand, if you don't mind. There are complexities to it, but we don't need to go over all of these because it's going to make understanding this for people who this is new to very complicated. All right? So I'm simplifying things. All right. So in the first processing layer, the input here, or source pixels, are going to be from an actual image, right? So a grayscale image with black and white pixels. Okay. So this convolution step, therefore, looks for a pattern in a group of neighboring pixels, like this, that, that corresponds to the pattern in the convolutional filter. Okay. So this filter, as I said, is sort of dark on one side and light on the other, for example. Now, this gives us a single value for this pixel here in the output map, this destination pixel. All right? But this same operation is done for every position in this map, in every position in the input, right? Each of which produces a single number to fill in all the cells here. Okay? So this is an easy computer operation, right? Because it's basically a matrix multiplication, this is very, very fast for computers to do. And it looks for every different position, how well it matches the filter. Okay. So, this is one example filter. But what's normally happening is that there are actually several of these happening at the same time in each layer. Okay. So here we've looked at just a horizontally oriented edge, right? But what we'd actually do in our network is have several filters in a bank that looks like this, all right? And each one of these is convolved with the image to produce a single output, all right? A single output map. And this basically says, okay, well, if I take this filter here, which let's say this one because it's a straight diagonal, right? Basically, it finds everywhere in the image where there are diagonal orientations present, right? But, of course, diagonal isn't the only orientation we care about. We also care about vertical. So we've got a separate output map for how much things, where there's vertical lines in the image, okay? And so on. Okay. So there's a large set of these different filters, right? And as it says here, they're all learned, all right? In this case, we're using kind of handmade examples, so particular edges. Right? This is a very, very simple way of looking at it. Actually, they're the targets for the machine learning in the network. All right. So the pixel in the resulting feature map, right, doesn't describe a pixel like this. Right? It basically corresponds to the amount of activation of a unit in this layer of the network. All right? So it's very important to stop thinking about this as if it's an image. Right? This is an image, the input. This is a pattern of neural activations, of unit activations of the units in a layer of a network. Right? It's easy to think of it as being like an image, but try to get beyond doing that as quickly as possible. Right? So a pixel in one of these feature maps represents the activity of a simulated neuron or unit. Right? And here we see 8 filters that have a large range of orientations. Right? The sizes of these filters are much larger than what we saw here. Okay, this is a simple example because you can work through it by hand. Right? This is a much larger group of pixels. Right? It's looking for a more complicated pattern, basically. Right? And on a larger spatial scale than we see here, which is only looking at 3 at a time. Okay. So, there are some variables that determine how this step behaves. All right? So first of all, we have depth, which is the number of filters that we're looking at. In the first example, we were just looking at vertical orientation, so that's one type of filter. In the second one, we looked at 8 different orientations. All right? So depth is basically the number of filters that we're looking at between each layer. Okay? The size of the input image is also going to matter. Right? The size of the filter, the number of pixels that little filter, that convolutional filter covers, also matters. That is the spatial scale of the features that we're going to be detecting. Also, we can look at the stride, that is to say how much spacing there is between the filters. As we looked at it, as we described it in this example, we're going to check this on every different possible position, but we don't have to check it on every possible position. We could, instead of looking at, this is a sort of one-dimensional example, instead of looking at this filter and how it corresponds to this 3 and then this 3 and then this 3 and then this 3. Obviously, there's a lot of overlap between those. So it's quite common to use something called a stride, so that there's basically a gap between the positions that you're looking at. Right? So here we're not looking at this group of 3, we're looking at this group of 3 and this group of 3 instead. We often put some zeros at the edge of the image for various technical reasons, just to make sure that the whole image is being processed, basically. Okay. And this gives us a particular number of filters. All right? So this is determined by all of these different parameters in this way. Okay. It's not important for you to know that equation. Right. Notice here that that computation that we're doing is linear. All right? It's just a multiplication between this and a group of input pixels. Right? Okay. So how is a convolutional neural network different from a traditional or fully connected neural network? Right. So here we can see a convolutional neural network, and what we're doing is we're getting this little filter, and so we're saying that this pixel only cares about the content of these 3 pixels. Right? And this pixel only cares about the content of these 3 pixels. Traditional neural network, a fully connected neural network, typically makes a link between every one of these layer 1 pixels and every one of these layer 2 pixels. Right? So everything is connected to everything else. Now, in a convolutional neural network, what this means is that the spatial relationships in the input matter. Right? If this is connected to everything, right, then the order of these doesn't matter at all. Right? Whereas if this is only connected to 3 neighbouring units, right, then the order of these matters a great deal. So spatial relationships are the thing that deep convolutional neural networks analyse. So they analyse where things have a particular relationship that's defined by a particular filter. So there's therefore a constraint on this spatial spread here that we do not see in a fully connected network. So that means that spatial relationships become important in a deep convolutional neural network in a way that they're not in a fully connected network. This constraint on the spatial spread between layers is particularly appropriate where the input layer nodes here have meaningful spatial relationships between them. Right? So what do we mean by meaningful spatial relationships between them? We'll look at some examples of that in a minute. In this image, in the image example that we saw earlier, right, the input image was a 2-dimensional image, the filter was a 2-dimensional filter, right, and the output was again a 2-dimensional image. Right? In this example, the filter is 1-dimensional, the input is 1-dimensional, and the output is 1-dimensional. Right? So these are doing different things. Right? So what's the deal with this dimensionality? Okay, so this is a really important thing to understand. So there are different uses of deep convolutional neural networks, and the number of dimensions in the input determines the number of dimensions in the filter. Different numbers of dimensions are suitable for different inputs and different tasks. Okay? But the principles involved here are the same regardless of dimensionality. So we're going to look at examples from 1 and 2 dimensions because they're easier to follow and easier to show in slides, right, on a 2-dimensional screen. So 1-dimensional convolutional networks are not appropriate for image inputs because in an image there are 2-dimensional spatial relationships that matter. But 1-dimensional deep convolutional neural networks are very useful for sequences, like sequences of words. All right? So, in the case of language, 1-dimensional deep convolutional neural networks become very important. Very often, these 1-dimensional inputs, the sequence is kind of a temporal sequence. Right? Now, this is where recurrent networks come in. We're going to come onto these much later, but recurrent networks are just useful to introduce here. So, what we're doing with a convolutional neural network is we're looking at a group of nearby inputs, right? So those might be the words in a sentence, right? And the filter spreads in both directions. Okay, so it looks at the relationship between a group of, let's say, words, right, and the words before them and the words after them. Right? That sometimes isn't an appropriate thing to do. A recurrent network does something a little bit simpler so that the activity of the unit only depends on the stuff before it and not on the stuff after it. That is to say that the units have a temporal memory. Okay? So that the activation of a unit depends on what comes before, but it doesn't depend at all on what comes after. Right? Okay. So in a 2-dimensional deep convolutional neural network, the main application of that is image processing. So that would be for things like object recognition, okay, for autonomous vehicles specifically where the sensors that they use have 2-dimensional outputs, so like images again. 3-dimensional deep convolutional neural networks, again, the principles are exactly the same as we've seen for 1 and 2 dimensions, but the input is a 3-dimensional image and the filter is 3-dimensional as well. Okay. These mostly come into play in 3-dimensional image processing. Okay. So, for example, medical image analysis, medical imaging often makes 3-dimensional images. So if we want to analyze those, we can't analyze them in a 2-dimensional way. 3-dimensional deep convolutional neural networks are sometimes used for image processing with a temporal dimension, that is to say video analysis. Okay. So there we're using time as the 3rd dimension, right? There's no, time is a really unusual dimension here because it's not like the spatial dimensions in a 2-dimensional image. Okay? So if I show you a video, distances in time and distances in space aren't the same unit. They're not the same thing, right? So the extent of a convolutional filter in the time dimension is typically completely different from what it's doing in the sort of 2 image dimensions. Okay. So time and space are in different units. They're in seconds and millimeters or whatever. 4-dimensional deep convolutional neural networks are really only used for 3-dimensional image processing with a temporal component, which is involved primarily in time-resolved medical imaging. Things like functional neuroimaging, functional MRI, produce 3-dimensional images and analyze how they change over time. Again, recurrent deep convolutional neural networks are sometimes used for that because generally only the past matters and the future doesn't for the interpretation of the current image. 4-dimensional deep convolutional neural networks where all of the 4 dimensions are image dimensions are also possible, but humans are 3-dimensional creatures in a 3-dimensional world, right? So this does generalize to higher numbers of dimensions, but because we live in 3 spatial dimensions, it's very, very hard for a human to think in 4 spatial dimensions. Right? This doesn't cause any problem for a deep convolutional neural network. This can scale up to any number of dimensions. That doesn't matter. So they're not limited in thinking in the way that humans are. Okay. So, so far we've looked at the filter operation, which is indeed a lot of what's going on here, and it's largely the most important one of these operations. Okay. The nonlinearity is introduced primarily by the threshold function, or rectification operation. And the goal of this operation is to only activate the output feature map if its value reaches a certain level or threshold. Okay? And that threshold is typically 0, because very often in these networks the filter that we use has a mean of 0, okay, built into it, which we'll come to in a minute. That's the normalized step. Okay. So that is to say, now if the activity of the filter operation, the convolve operation, is below 0, we're just going to set it to 0. If it's above 0, we're going to increase the output as the input increases. So for any input value above 0, the output, in this case, equals the input. So this is this introduces a very simple nonlinearity around 0. All right? This is a linear function, this is a linear function, this is where the nonlinearity is happening. Okay. Other activation functions can also be used to map the input and the output of the threshold operation. But in deep convolutional neural networks, this is so common, just doing a split at 0, that this is often just referred to as a rectified linear unit, or RELU. This is going to come up a lot in your lab exercise, this term, right? And this is all it means. It means anything below 0, no output, anything above 0, linear with the input. Okay. So this is so common in the implementation of deep convolutional neural networks that it's barely worth discussing any other examples. But one issue with this function is that it has no maximum output. Right? And this is very bad for simulating biological systems, because biological neurons do have a maximum output. Right? And so, if you're simulating a biological system, we also very often introduce a maximum here as well. Okay? So the output increases with the input up to a certain maximum activation. Okay? In practice, the maximum firing rate of a biological neuron is very rarely reached, okay? But this is sometimes included in networks that are particularly modeling biological brains. So, as a result of the filter operation, the... question. Is ever learned? I'm sure people have done it, but we're not going to use anything where it's learned. So, as a result of this filter operation, the response in each unit depends on several neighbouring units. Okay? So the units after filtering respond within a certain area of the input image in this case, though as I say, it's not going to be an image when we get to later stages here. The activation of neighbouring units is therefore often going to be very, very similar, okay? Because they're looking at very similar parts of the image, or overlapping parts of the image instead. So neighbouring units often represent very, very similar information. The pooling operation therefore downsamples the units to improve computational efficiency. So this is again best explained by an example. So here, what we've done is we've got this image of the number 3, okay, and we have split it up into lots of different orientation filters. Okay, so we've gone from one image to 6 images. All right, so this has become a lot more computationally intensive straight away. And then so we're going to subsample that so that we make these images simpler and just take up less space. All right? And then when we do the next convolution, we're going to end up with even more, right, filters and even more feature maps, so different transformations of this initial image. So that causes basically a computational explosion, right? That as we add more and more layers, each of them are transforming a single representation into multiple representations, so we end up with just very, very, very deep, thick representations of our input space. Okay. So to avoid this explosion of computational load, it's very important to reduce the size of these images. So what we often do is we sort of downsample from, in this case, a 28 by 28 image, right, to a 14 by 14 image before doing the next convolution. Okay, and then we downsample that to a 10 by 10 image, and so on. Right, so that we're making the more and more filters, more and more feature maps, right, from a single image, but we're making them smaller and smaller and smaller, right, to deal with this problem of computational load. So the pooling operation is typically a very simple operation, a max operation. Okay. So if we take the maximum of a square of 2 by 2 here, right, this is what we're going to use to fill in this here, right. So it's going to go through a few times, but you can see all it's doing is picking up the maximum from each of these. And that is an operation that's very, very commonly used. So this operation, because it's kind of downsampling the information, it looks a lot like changing the stride parameter that we saw earlier. Okay? So here we've got the filter is positioned at every location, right? But we could just position it at every second location instead, and that would do something very similar. It's important to understand the distinction between those. So increasing the stride may actually miss the maximum unit. Okay? So here, look, if we've got this multiplication produces -2, the next one produces +2, right? And then the next one produces 1. So if I was to look at the maximum of these three, the maximum is this 2 here, right? But if I just do it by changing the stride, right, by making a stride of 2 each time, right, then we're going to miss these maxima here. So effectively we drop some detail by using stride instead of pooling. Right? And as computers, so the reason for using stride instead of pooling is that it's more efficient. Right? You have to do less convolution operation, and you can skip the pooling operation. Right? But as computers and deep network implementations become faster and more efficient, it becomes less necessary to have pooling between layers, and it becomes less necessary to choose stride instead of pooling, and therefore drop some detail. Yeah. Yeah, it is sometimes, yeah. This is just a really simple example to sort of get the point across, but indeed sometimes it does use like a 3 by 3 square instead. Okay. So the threshold and pool operations that we've just seen both use max functions, all right? So as a result, even if the convolution filter has a mean of 0, all right, then by the pool stage, we have mean activation above 0, okay, with quite an arbitrary range as well. Okay. So furthermore, this range of the representation that we have after pooling is going to change considerably between feature maps, effectively weighting some feature maps to contribute more to the result than other feature maps. Okay. Subsequent layers have a problem here, because subsequent filtering steps operate across multiple feature maps, and ideally those should contribute evenly, rather than being very different. Okay. So the normalization operation linearly scales the data to have a mean of 0 activation. Okay. So here we've got this data, we've just moved it so its mean is at 0, right? And to have a unit extent. So that is to say, here we've got 2 different dimensions, right? And here they're scaled so that the extent in both of them is the same. So therefore, the first step in, we've got a little equation for this. The first step in normalization is typically to subtract the mean, okay, which is what we're doing here. We're subtracting the mean in x and y to bring it to the centre here. Okay, so that 0 now becomes the mean. All right. And then the next step is to divide the result by the standard deviation in each dimension. So this is what we see here. Okay. So this makes the data have a mean of 0 and a standard deviation of 1. Okay. This is necessary for both theoretical and practical reasons. First, machine learning generally assumes that data reflects measurements of independent and identically distributed variables. You may have come across this term IID before. And normalization forces identical distributions. Second, if the activation function depends on whether a unit's response is above or below 0, as we've just seen it does, then having 0 mean inputs and 0 mean filters means that about half of the units will have a positive activation and half of the units won't. All right? So this means that half of the units are active and half of them are inactive. All right? And this even split between activation is a very efficient way to store information in a network of limited size. Third, having the same range for all feature maps and layers means we can have the same maximum threshold and the same activation function throughout the network, right, without having to change it because the data doesn't anymore fit with the assumptions that we're making here. And fourth, as a result of these considerations and other sort of minor technical points, training rates are far better if you include normalization than if you don't include normalization. And the classification accuracy, which is what we see at the top here, is also much higher as a result. So even without normalization, you can basically never reach the same performances that you get. Okay. So now we've done one layer of a deep network operation on an image. So let's summarize it. We've used the filter and convolve operation to determine how well each group of nearby pixels matches each of a group of filters. All right? We've used the threshold or rectify nonlinearity to induce a nonlinearity by setting negative activations of units to 0 and maybe also set the maximum activation. We've used the pull step to downsample the units and therefore improve computational efficiency. And we've used the normalize step to rescale the responses of each feature map to have mean 0 and standard deviation 1, so that each feature map contributes similarly to classification and what the next stage is doing. So, in a deep network, though, there are several layers performing similar operations or transformations of features, all following these same principles. Right? And subsequent layers generally use the same operations in about the same way. But the filter and convolve operation differs quite a lot between the first layer, which is the example we've seen, and subsequent layers. So far, we've only looked at the first layer, which is the simplest. In the first layer, we're convolving a two-dimensional input with a two-dimensional filter to give a two-dimensional feature map. But if we do this for several filters, then we end up with multiple feature maps. All right? So the next layer effectively becomes 3 dimensions. It's got a third dimension, which is different layers of these feature maps. So the third dimension basically corresponds to the different filters that we're using here. So in subsequent filter operations, the filter becomes 3-dimensional and crosses all of these different feature maps. So it's looking for a pattern across all of the different feature maps together. So it gives a response at a single point that depends on the activity in this whole group of units here. So remember that this is a result of a matrix multiplication, so this is going to be a single number regardless of the size of the inputs that are being used. And in fact, this is even true for some input images. So colour images are often treated as 3 dimensions, with the third dimension being the 3 different colour channels. Okay? So for colour images, the filters used are also 3 dimensions, right, and are potentially have different spatial responses required from each colour. Okay? So we can see the input image as a special case of the inputs to all layers. So in this case, look, we're looking at, we have a filter that's looking at 3 different layers here, which are the red, green and blue channels. So the input image is a really special case of the inputs to all of these layers. And as we see here, as we go up these different layers, right, we go from a really shallow representation with relatively few feature maps to a very deep representation with lots of feature maps but a very, very small size. Right? So it's really downsampled the image a lot to pick out the relevant features. Okay. So as we get higher up the network, these filters become harder to understand in two important ways. First of all, the filter shape crosses multiple independent feature maps. Okay? So an edge detector applied to an image is a pretty easy thing to understand. It's easy enough to conceptualize. But with a high-dimensional filter crossing several different transformations of the data, this becomes extremely difficult for humans to think about. Okay. Second, the input feature map becomes more and more abstract. That is to say, it gets very hard to conceptualize what feature is being represented. Okay. As I say, there's a tendency for humans to think about these as images, right? But they're not images. Okay? They're activations of neural networks, right? So try to avoid visualizing them. It just leads you in the wrong direction. But what we're doing then is we're analyzing with these later layers, we're analyzing the patterns of activation in networks. We're not analyzing images anymore. So it becomes very, very misleading to think about them in terms of images. So it's very hard to conceptualize these abstract higher order patterns, but conveniently we don't need to do that. The computer can do it for us. For a computer, all of these are very, very similar operations. Okay. But it is important to understand that deep networks have increasingly complex representations of the objects in images. And over several network layers, we see that the representation goes from being relatively simple to being really, really complicated. So to get a feel for what features are represented in different layers, or what features might be represented in different layers, there's a trick known as inverting the network, which is basically activating different feature maps and their connections back to the original points in the image to say sort of what does the representation in this feature map look like. Okay. So here we've got an example of an input image. Right? Here we've got kind of the edge detected version of that. And we can see lots of parts of the image where the edges are emphasized, so straight lines are emphasized. If we go up to the next layer, we can see that conjunctions between edges are emphasized. So here we can see lots of corners and squares coming out, and lots of gentle curves coming out. As we go to yet a later layer, we see this transformation has lots of circles in the representation. So it's pulling out more and more complex features, right? And these circles are present in the original image, but the early filters are generally doing edge detection type things. Right? So successive layers are finding increasingly complex relationships between points in the original image, following correlations found in patterns in the original image, but also correlations in the patterns of neural network activity in earlier layers. Right. So what we've seen so far is that the filters that we're using here generally have a single set of weights for all positions in the feature map. Okay? So we're using one filter at all of the different positions. And this is good because if a feature is useful to compute at one position, it's probably going to be useful to compute at another position. Right? Second, the filter values are weights that need to be learned. So it's very computationally demanding to do this if the set of weights is too large. So if the filter is changing across the image, this becomes extremely computationally demanding to do. And also the convolution operation is a very, very fast matrix function. But if the filters aren't fixed, then the convolution operation can't be used. Right? So we're going to see that these are big constraints that don't apply in biological deep neural networks. So the higher we get in the network, the more spatial integration occurs as the result of repeated convolution and pooling. Okay, so we go from big image to small image with lots of layers. Okay. At the same time, the number of interesting feature combinations, so that is the different feature maps, increases. So the feature maps become increasingly narrow but increasingly deeply stacked. Okay. And at the end, some classification needs to be done on the pattern in here, right, to make a decision, which is the fundamental goal of the network. Okay. At the last stage of the network, after several convolution and pooling steps that we've looked at in some detail, this last layer of the network uses a fully connected network for classification, so to work out what the image was. Okay. Here, the spatial relationships are discarded. Right? So the spatial relationships that we're seeing here are discarded, so that we just end up with a lot of values of the activations of all of the units in this cube here. Right? So then we use a fully connected network to pull out any pattern among these units, right, that might have something to do with what type of image was being shown. Right? This is a fully connected network in this last stage that does this last thing. Right? So the activation of this top layer of units here is simply associated with a particular type of object that has previously made a similar type of activation. Okay. Yeah, that's what's going on here. So the activation here, right, in this fully connected layer can find any pattern in these output images because these spatial relationships have been discarded. Okay. So after doing that, what we need to do is go from this activity pattern in this fully connected layer here to a decision about what object was being shown, right, in this case. So the weights through our network are going to basically produce a pattern of activations of the last layer. So in this case, it's just 3 cases, right? What we want to do is find the one of those that is most likely to correspond with a particular type of image that we've seen. So what we do is basically we find out which has the maximum activation, right? So it's this one, because this is the sort of score of each of the possible outputs, right? We find which one's the most likely, and we choose that as our winner. That's the decision that we make, okay? And this score is typically converted into a probability. So look, we've got all of these scores here that add up to 3.1, right? These need to be converted into a probability of each of these possible 3 outputs, right, that add up to 1. And this is done using this equation here. That's a normalized exponential function, but that's not particularly important to you to understand here. So this last step, the softmax operation, is basically converting the activations of the sort of scores given to each of the possible outputs to a probability that that is the right output. Right? And what we're generally going to do is just take the winner of those. But it might be that 2 of these have high numbers, and then we're not really confident what the answer is. Right? So this gives the probability that each of these is the answer, and it's actually somewhat artificial to pick the one, right? It gives the probability for all of the possible answers. All right. So far, we've carefully ignored what filters are used in these higher levels and only looked at sort of hand-designed filters in the first layers. So it's straightforward for a human researcher to design a simple filter like an edge detector to operate on an early layer like an input image. But when we get to more abstract filters, operating over multiple feature maps whose responses are already difficult to conceptualize, humans can no longer effectively design the right filter. Instead, the filter structures are the target for machine learning. Right? The convolution filters are the main links between the different layers of the network. So they effectively form the weights of connections between the nodes in a neural network. Right? So here the nodes are pixels in a feature map, or really more accurately put, activations of individual units. So to learn the weights of these connections, the network needs to learn the structure of the filters. Here we constrain the filter's size to be a particular maybe 3x3 or 5x5 group spanning all of the feature maps in a layer. Okay? But the filter's structure, the weights from the different pixels across the feature map, has to be learned. Right? So we're only constraining how big the filter is. We're not constraining the values within it, basically. Right? So as we've seen, a filter is a limited group of connections, so the learning is much simpler than in a fully connected network. But just like in a fully connected neural network, this uses backpropagation of error, which is a mathematically complex process that is notoriously difficult to understand and explain. Okay? I'm going to simplify this as much as possible. I've been simplifying everything as much as possible. But this really reaches the limits of how much you can simplify it. Backpropagation. It's a notoriously horrible thing to understand. Right? So what we do to start is we have a new observation, so a pattern of pixels, let's say, at x, a group of values at x, and we have a target, y, which is what we want. All right? And so that's the ideal, this y asterisk here is what we want. So what we're going to do then is we're going to pass our inputs through the network using the weights that we have already learned, all right? And pass it through all of these stages, and this is going to come up with a prediction, all right, of what y might look like. And we're going to compare that to the y that we actually want. Okay, so we're going to compare the predicted output to the output that we actually want. And this gives us a prediction error. So that's the difference between the prediction and what we actually observed coming out of the network. Sorry, the prediction that we observed coming out of the network and what we actually want. That tells us the amount of error in our network. Okay. So then, what we do is, this is where it gets horribly complicated, for each unit in each layer, okay, we look at how well should this unit's activation be higher or lower to produce the output that we actually want. Okay. So what's the difference between the activations and kind of the ideal activation that will produce the right answer? So, then, how does this change? How does the output here, so if we start with changing this one, how is this going to affect this layer, right? And are these activations too high or too low? So this backpropagation is happening at all of these layers simultaneously, which is part of why it's so difficult to understand, because all of these differences between what we observe and what we want as the activation at each layer are all connected and they all relate to each other. So basically then, if we find that this G activity is too high, right, we can look at everything that affects this G's activity. So here, these inputs, right, are these too strong or too weak, right? So then we can change the strengths of these connections, which are effectively the pixels in the filter that we're looking at, such that we get a closer G. And we can also do that for these connections here, so that we get a better representation of this H layer that gets us closer to what we want for Y here. So closer to what we want for the output. Okay. So that's effectively what backpropagation of error is doing. It's looking at how the network can be adjusted to produce the right answer, right? And it's going to make that adjustment depending on how wrong the answer was. Okay? Right. So that's the intuitive way of understanding it. There's a shitload of maths behind it, and I don't think that's important for you to understand, because guess what? A computer's going to do it for you, right? You'd be an idiot to do this with a pen and paper. Okay. So it's not super important to understand how to do this. Google's made a lovely way of doing it for you, so you don't have to worry about it. All right. Yeah?
Now, is the Y here like an actual object?
Yeah, so this is exactly, it's what you want the Y to be is 100% this is the object that I'm seeing, right? But what it will actually be is a probability that this is the object that I'm seeing, which is never going to be 100%, but it might be as low as 10%, right? So
we're not actually learning the filters, or at least the individual layers.
No, you're learning the connections between the layers by determining whether those are making the predicted activations of the units within all of the layers right or not, right? Okay. Which is really summarized by what you see at the end. So, all right, last slide, just to summarize everything. These are we've covered a lot, and these are the really important things for you to sort of take away from this, right? Deep convolutional neural networks are useful for achieving tasks that are difficult to describe formally. That is to say, tasks that are very difficult for computers to do, but often tasks that are relatively intuitive for humans to do. So this is a form of machine learning that performs multiple sequential nonlinear feature transformations in hierarchical layers. Between each layer, so between each feature map layer, there are a few simple operations. So convolution checks each position's match with a specified filter kernel. Okay? Thresholding introduces a nonlinearity. That's the main thing it's doing. Pooling downsamples the image, typically by taking the maximum, to just avoid the representation getting too big. Normalization rescales responses so that each feature map contributes similarly. A final fully connected layer links the patterns of the most abstracted top-level features to the required response, right? The softmax operation then determines the probability of the desired response, and then the match or the conflict between the expected and actual outputs is the basis for backpropagation of error, which, as I say, is a very complex mathematical process which adjusts the structure of the filters, which is the link between the layers and therefore the machine learning target. All right. So those are the main important points for you to understand from this and take away. If you found all of that really straightforward, because you already know a lot about deep convolutional neural networks, the next class is going to be almost entirely about biology. So it relies on a completely different skill set, right? And you're going to learn some very different things, but hopefully you'll also learn the relationships between them. So for those of you that found this really difficult, you'll probably find the next class a bit easier because you might come from a more cognitive background. If you're the other way around, you might find the next class a lot more difficult. All right, so see you on Friday at 9:15.